Speaker of the next session is Suman Chatterjee from NCRA TIFR. He's going to talk us. He's going to speak about H1 intensity mapping.
Thank you. So, yeah, talk will also be generic. I think I'm audible. Okay. So I'll give you an brief overview of the H1 intensity mapping. What are the prospects? How is the progress going on, and what are the challenges? Okay. So just to set the tone, like we have heard till now that the signal, there will be no 21 centimeter signal coming from this region, that is from CMB to up to redshift of 150, because CMB is coupled to the spin temperature. And after that, when CMB decouples from the spin temperature, we will have a signal, and probably 21 centimeter signal is the only one signal in that particular epoch, and that is called dark ages. Moving on, in the redshift range between 30 to 6, about which we have heard till now, is the epoch of reionization and cosmic dawn, and this is where the phase transition happens in terms of H1. So this particular epoch is primarily dominated by very complex astrophysics, and this epoch promises to probe about the first stars and the galaxy form, how the IgM has been ionized, and so on and so forth. So there are, unlike dark ages, there are other probes of this particular epoch are emerging. And finally, when the intergalactic medium is completely ionized, we heard that in the redshift range beyond below 6 or something, we have the H1 residing in dense clumps, which are basically the galaxies or Camp-Lyman alpha systems, and these shelf-filled H1 clumps basically holds the neutral hydrogen in the this post-reionization era. This post-reionization era is suitable for a probe of cosmology, because it can track the density fluctuations, and it can probe the galaxy for information, and finally it also can probe the BAO and dark energy, so on and so forth. So I'll switch gears. So you have heard talks on this particular epoch till now. So I'll switch gears and I will focus on the post-reionization era. So what is the first step that you do when you move on to post-reionization? And you take a telescope and find out where the H1s are. So this has been done for like last few decades, and they have found that it is so these surveys primarily sort of try to find the H1 in the galaxy, and they have seen that it's really difficult to image or map the galaxies up to very high redshift. So like there has been a detection up to at like redshift of 0.4 for a single galaxy which has H1. So we need to devise. So first of all, we need to understand how much H1 is there, but we cannot do this by directly from observation. And as SK is coming up, we will be focusing on redshift beyond 1 or something. So we need to take refuge on the simulation to at least get an idea how much H1 will be there in these galaxies, and how we can best probe this particular H1 signal. So to do that, I will prescribe a simple prescription, but there are complicated ones and there are more simple ones. I will do something intermediate. So one can start with a simple dark matter simulation. I have put some name as an example, but you can start with anything. And then once you get the dark matter distribution in your computer, you can identify the halos, and then you do this whole thing for different redshift to get the history or the merger history of these halos. Then you employ some sort of galaxy formation model, whose parameters are being taken from different sorts of local observation you had, and you get a model of these galaxies and their properties. So once you have this, you make a galaxy catalog, and you infer different H1 properties of those galaxies from this simulation. Okay. So once you have these inferred properties, you can now try to see how you can estimate with these signals with the upcoming SKA or any other telescope. So, right. So this is just an example. So it seems that it's still hard with SKA to detect a single galaxy. So as an example, I have taken one particular sort of galaxy, and this shows the frequency direction distribution of the gas, and it will, so for this particular amount of hydrogen mass in the galaxy, it is like it will take about 500 to 1000 hours of observation to detect a single galaxy, which is enormous with SK also. So can you do better than that? So it turns out you can do stacking of these H1 galaxies. So you have a companion galaxy survey, you know where your galaxies are, you take your observed H1 data cube, you stack those positions, and you get a measurement of the H1 that these galaxies contain. And this has been done with UGMRT at quite high redshift compared to other sorts of detection. So however, there is a caveat. So the caveat is you lose the distribution information of these particular H1 clouds. Okay. So for SK you can do this, and you can do this within 100 hours of observation. But again, like, you will lose the information about the clustering of this H1 and other stuff. So we come to our the main topic of this talk, and which is intensity mapping. So we have seen that it is very expensive to identify each galaxy and do a cosmology. That has been done in UV cases, and we have seen that if you stack the galaxies, you lose a lot of information about their clustering and other. So what we do, so we do intensity mapping. So in intensity mapping survey, we do not need to identify each galaxies in the field. So we have a very coarser resolution observation where we collect. So basically, the collective this 21 centimeter redshift signal coming from these particular H1 cloud appears as a diffuse background as shown here, and their clustering is imprinted on these regions, and this is how you get the H1 content of this particular epoch, and also the clustering information of this particular epoch. So how do you do the observation? So as H1 is a line emission, you do this intensity mapping experiment at different frequency values, and that gives you the information regarding how the H1 evolves in different redshift. And so this is basically shown here. And in the Fourier space, these particular density fluctuations will be sort of coordinated by this k perpendicular direction, which is the plane that is perpendicular to the line of sight of the observation that we are doing, and the k parallel of the Fourier or the Fourier modes, which are along the line of sight of our observation. And from these intensity maps, sorry, it's a 40-minute talk, right? Sorry, I just started and you said finish. So how long it's been? Okay, sorry. Yeah, and from these intensity maps, you can get the power spectrum for this particular sort of H1 distribution in this box, and this power, from this power spectrum you can work on different aspects of cosmology. So once you have an idea how you have modeled your how your intensity maps are, then you turn your head and you say, okay, I want to model my power spectrum with some reasonable parameter. So the primary assumption is that these H1 are the bias tracers of underlying dark matter distribution with a bias BH1, and the power spectrum has also effects from redshift space distortion and finger of God, and the matter power spectrum is here. So so from an intensity mapping experiment, you get this power spectrum measure, and different experiments would like to is trying to measure this 21 centimeter power. So these experiments are divided into basically three categories. So one experiment which are called interferometers. They are an interferometer with multiple antennas working looking at the same field, and they can have a high resolution. Whereas there are antennas, those interferometers are like chime, proposed hierarch, Tianlai, GMRT, etc. Then there are another class of experiments that can be operated as an interferometer or a single dish depending upon your requirement. These are all listed here. That is Meerkat in South Africa and ASCAP in Australia. And finally, the old players in this intensity mapping games are the single dish instruments, and they are this GBT and PARS. Okay, so but I should mention that so these two types of instrument measure a two different regime of the power spectrum. So if we talk about interferometer, what interferometer does, it takes signals from two different antennas pointing at a particular direction, and the length scale that is the resolution of this particular sort of experiment is decided by the maximum separation of this two antennas weighted by the frequency wavelength of the observation. Okay, whereas for the largest scale that it can observe is defined by the diameter of a single antenna. Okay, so your measurements will be somewhere in between diameter of the single antenna and the largest separation between two antennas. Whereas for the single dish, you have only one dish, so the characteristic length is the dish diameter, and this is your like resolution of the intensity map. So once we have sort of understood that which are the regimes we can observe with this particular sort of instrument, we can look into the power spectrum, and we can see that for the single dish experiment, we primarily try to hunt the large scale region of the power spectrum, which sort of encodes the redshift space distortion effects and cosmological information, whereas the interferometer sort of goes to the medium to small scale of the power spectrum, and which contains the information of BAO, nonlinear galaxy formation, etc., and cosmology. So when we discuss these two type of experiment, we should keep in mind that we are playing in different regime of the power spectrum. Okay. So for SKA, they have proposed, they have done some analysis, and this is the this sort of power spectrum power spectrum and their error you would expect in the very low redshift range, and in the SKA low you can get sort of this type of error and the power spectrum, and these estimates promise us that they can separate between two different dark energy models, and they can also put a limit on the dark matter and neutrino mass, etc. Okay, so and from the interferometric from this intensity mapping perspective, they can also try to probe the global H1 density, and which in turn will lead you to different galaxy properties, to infer in the different galaxy properties. Okay, so this discussion is incomplete without the challenges that you face during this intensity mapping observation. The primary challenges are the following. There are extragalactic point sources which you can remove up to some level, but the diffuse foregrounds are extremely hard to remove from the observation. Okay, so I will focus on foregrounds in a minute. So instead, and on top of the foregrounds, there are noise. Uh, However, that can be sort of taken care of during using different longer integration time and different sort of unbiased estimators. And there will be different instrumental errors. So Jayesh will talk about these things. And RFIs are a nuisance, and we do not have a handle on those. And finally, there is also ionosphere. Sorry, spelling mistake. So ionosphere is also a nuisance to us. So I think there will be a talk by Obhirup Datta regarding this. Yoshunda won't give the talk. So Obhirup Datta will give a talk on this challenges in detail. Okay. So concentrating on the foreground. So there are two different techniques that people use to tackle the foreground. One is foreground subtraction, where you subtract your foreground contribution from the observational intensity map, and there is foreground avoidance. So foreground subtraction is primarily till now done in image plane with some blind foreground subtraction techniques that are basically some sort of component analysis, and some model feeded foreground subtraction technique has been developed recently, but primarily it has been applied to UR data, which is Gaussian regression process. Okay, so the more sort of conservative approach is foreground avoidance. So so we have from different observation we have seen that the foregrounds are smooth in frequency, and this sort of is reflected when we estimate the cylindrical power spectrum, and this foreground is expected to be restricted within this so-called foreground wedge, and it is expected that the beyond this region, beyond this wedge region, we will have a cleaner window to estimate the power spectrum. However, different instrumental effects, which you will heard in later talk, can also like potentially uh, spill the foreground contribution to this particular region and messes up the observation. So this sort of shows how the foreground contribution and the signal looks in the cylindrical power spectrum scenario in case of a post-ionization intensity mapping experiment. And as you can see that this is the way, this is how you expect your H1 signal to be, which is smooth, which doesn't have that much feature in power spectrum level, whereas your different foreground component, that is galactic synchrotron emission and EPS, will have a distinct feature, and we try to avoid those regions to get a better estimate of the signal. Okay, so this has been done from the people around here, and they also found that it is difficult to get a signal out of this particular sort of observation, and they have also found the wedge and the spillover in the wedge beyond the wedge. So they have taken some region and estimated an upper limit in this post ionization 21 centimeter intensity mapping signal. Okay, so you will hear for this particular topic on Srijita's and Asif's talk. Then you will have so this sort of technique also has been tried using single dish. They also so this is an observation by the GBT team, and they also found that although they are doing a independent component analysis and foreground subtraction, they also find that their recovered power spectrum is systematic dominated. Which are here. Okay, so they also cannot detect 21 centimeter signal in autocorrelation. So it's really challenging to detect the 21 centimeter signal in autocorrelation. So community has taken refuge in case of with cross correlation. So primarily these cross correlations are done because we believe that the systematics are of two different observations like galaxy surveys and 21 centimeter intensity mapping observation are uncorrelated. So when you cross correlate these two signals, you expect the residual foregrounds that are left after this sort of foreground subtraction, or the different systematics that create nuisance in 21 centimeter signal extraction will be cross correlated out, and this way we plan to mitigate this particular 21 centimeter nuisances. However, there is a catch. So the primary catch is that we expect to measure the 21 centimeter signal from redshift of something like up to redshift of 5 or something, 5, 6, using this particular intensity mapping technique. But to do a cross correlation, you need a companion survey like galaxy survey or QSO, and these are not available in high redshift. So this sort of sets limit on the cross correlation type of experiment. And finally, the modeling of this cross correlation power spectrum and others are pretty complicated, and some of the parameters you still need autocorrelation to recover. Okay, so this has been done using single dish experiments with GBT for long back, and they have found the cross correlation signal, and they have given us a bound in this particular parameter, which is a large scale parameter. So then I have mentioned that there are two different instruments that can be worked as in a single dish mode and an interferometric mode. So Meerkat has done, although Meerkat it is a SK Pathfinder interferometer, but they have measured the cross correlation signal in the redshift range 0.4 to 0.5 ish in a single dish mode, and this was a very short observation, if I remember correctly, few like tens of hours, and they have detected the signal. Okay, so the cross correlation signal has also been detected in interferometric mode, and that has been done by Chime. However, as you can see, this plot is a bit different from the other cross correlation plot you have seen, because they do not have the spatial resolution to identify galaxy position. So they did the cross correlation in the line of sight direction, and this basically shows how your signal changes as you move from the rest frame of the particular galaxy you're talking about. And they have, so we have seen that interferometric observations can model the galaxy properties and other stuff, so which cannot be done in principle. It's difficult to do in single dish observation, and they did the same. So they have this complicated power spectrum model where the galaxy properties are sort of encoded here, and the cosmological properties are here, and they have some sort of constraint from this particular cross correlation experiment in this set of parameters. Okay, so sorry. So how much time do I have? Plenty, is it? Okay. So regarding the future of so what SKA promises us in terms of future. So there will be two SKA facilities. One is SKA mid and one is SKA low. One SKA mid will be there in South Africa, and a Pathfinder is also in place. And this measures this is suitable for post-ionization observation. It goes from very high frequency up to 350 megahertz of the frequency, and this prediction here shows the estimates of the future constraints on the vanilla lambda CMD CDM parameter coming from SK observations in the SK mid section. Okay, so we can see that from it can jointly with Planck and other observations, it can do a better constraint on the cosmological parameter uh, in future. So what else comes in the future? So SK is primarily built in the southern hemisphere of the Earth. So to develop the radio astronomical instruments in the northern hemisphere, there has been a proposal to add few more antennas in the GMRT, and which will in turn give you a better estimate, better handle in the baseline space, because currently the UGMRT has very few short baselines, which can in turn give you an estimate on the large scale power spectrum. So this development is proposed in two different phases. So first they will put some antennas in the central core region, which give you a dense baseline distribution in the core section. Yeah. Yeah, that is the facility. Somewhere here. No, Planck result is somewhere like this gray one. You'll get some better handle. H naught tension, yeah, it's a long answer, sort of. Okay, yeah, I'll give you an answer. Okay, yeah. So this has been proposed in two phases, and so in this case, you will get a better sensitivity on the core region, and which will give you better estimates in the large scales, whereas this particular full upgrade will give you an better estimate in a holistic way. So we have done some Fisher matrix analysis to consider what is the how long it will take to observe this signal when you have this particular sort of expansion. And we have seen, so this plot here shows the Fisher matrix estimate to detect the signal, combining all the K modes available. And these three panels here show the estimates for a case of foreground avoidance. And the leftmost panel shows when you do not have any foreground, and the rightmost panel shows when you have foregrounds up to the wedge. And this particular post ionization band has been subdivided into multiple bands whose redshift are shown here. The subdivision is being done just because of the fact that signal evolves, and it is not reliable to consider very large band for your estimates. And this shows that even in a sort of pessimistic scenario, you can have a detection within a reasonable hours of observation, which is under 1,000. Okay, so what else? So coming closer to heart, so there is another experiment that is being designed, and sort of like the instruments are all in place, and we are sort of working on it. So this shows the estimates for this particular linear interferometer, which is OFA. It's called UT wide field array, and it works at a nominal frequency of 325 megahertz, which translates to a redshift of 3.35. And we have predicted that it will take definitely longer time to get the signal. However, this telescope can be used as a dedicated post VOR intensity mapping experiment. And with the beam uncertainty, so these two panels show the beam uncertainty in the particular modeling we use. So leftmost is the best possible scenario and rightmost is the worst possible scenario, and your prediction will lie somewhere in between them, and you will need about 1000 to 4000 hours of observation to get a decent detection of the signal. So finally, then you can actually, there are different QSO spectra that are coming up. There will be Lyman alpha forest observation, and they are planning to do tomography with this particular sort of system. So as it has been discussed earlier, so these features in the Lyman alpha spectrum are basically the H1 absorptions, and this can in principle probe the H1 in the post-ionization era. So we have estimated some number to observe this particular cross correlation signal at redshift of 2.5 with some reasonable hours of observation with different existing and upcoming telescope. However, it depends on like how good your observation is, means QSO observation is, and it depends on how much line of sight you get from your observation, which can actually sort of sample the 3D intensity mapping space for you. So with SK-mid, the signal to noise ratio estimates are very high, and you will get like 10 sigma sort of prediction with this very poor line of sight existence also. So to summarize this thing, so I have basically gave you an overview that 21 centimeter intensity mapping in the post-ionization era is an important probe of cosmology. It's an effective and cheap way to do cosmology in this particular era. It can also probe different galaxy properties at high redshift, and finally, the foregrounds are the crucial challenges towards detecting this particular signal, and autocorrelation measurements are still going on. We haven't been successful on this particular observation. However, there are different cross correlation measurements available, and in future with SK, we hope that we will get better results soon. So I am done. So I kept a few talk a bit short so that we can have a sort of interaction, because I guess showing more results won't sort of be helpful. So yeah, I would like to take questions. Yes.
Hi, Suman. It was a nice talk. Thank you. So my question is, can you go back to the, yes, is that Lyman alpha forest thing? And what did you do here? You cross-correlated your 21 centimeter with Lyman alpha forest or
Yeah.
DLS?
Lyman forest. So same field will give you 21 centimeter signal in emission and absorption in Lyman alpha.
True, but not sure how much strain will there be in the Lyman alpha forest field, because those are like kind of fluctuations in the intergalactic medium,
Right.
right?
So your 21 centimeter intensity mapping is also fluctuating.
No, but in
no,
post
it's not in the intergalactic medium, right? Your intergalactic medium is ion. These are some dense clumps that reside in your line of sight.
I'm not sure, but anyway, sorry. And yeah, so this was my question. Sorry.
Suman, yeah, thanks for this nice update. So two quick question, maybe, if that's okay with the other Suman. One was, you didn't say anything about the short noise. So
yes.
Can you comment a bit about that?
Yeah, absolutely. So Yeah, I should start here. So, although we are measuring a diffuse signal, it actually comes from discrete sources in your field of view. So, your H1 clouds are actually discrete, and so they will have a Poissonian sort of effect in the power spectrum. So, what will happen? So, basically, it will create a floor in this power spectrum measurement, beyond which you cannot have any clustering information available to you, and that floor actually actually encodes uh, properties of the particular galaxy mass function, and you can actually estimate like at different redshift where that floor will be. So there has been two sorts of proposal. It sort of limits up to what wavelength you can measure the clustering. Also, if you do not measure the clustering, from just a measurement of the floor, you can have some estimate of the H1 means the galaxy properties that you have. For that, they have some models. I can show you.
Thanks. Just quickly then about your cross correlation results from Lyman alpha, you predict that a measurement should be possible with UGMRT also.
Yeah, but
so I just wanted to understand. This was Lyman alpha forest on quasar sightlines.
Yes.
But now you can do tomography using Lyman alpha forest in galaxy sightlines. So
but
maybe have
we
you?
wanted to. So
I mean, if you can measure it there, then you should be able to measure it amazingly clearly using cross correlation with galaxy sightline tomography.
right, but like we wanted to do it on higher redshift region where the galaxy surveys are sort of like sparse, I would say.
Maybe we can talk about this.
Sure.
So I have a question, Suman. So you showed a picture where you have UGMRT and EGMRT. Can you go to the slide? And there are three cases: optimistic, pessimistic, and moderate.
Right.
So can you please elaborate the differences between these three cases?
Right. So let me take you here. Yeah, this sort of can elaborate. So optimistic is that this cylindrical power spectrum space is completely available to you. All the K modes are available. Okay. The moderate scenario tells you that you have your foregrounds up to thrice the primary beam. So these nulls are coming from side lobes in the primary beam. So we say that okay, my foreground extends up to third null, and beyond that there is no foreground contribution. And the pessimistic scenario is somewhat here, which sets by the horizon level. So you have your foreground still horizon, and beyond that you can all the K modes are available to you.
Thank you.
Yeah. So just to comment on Girish's question, there is a cosmos field where you have there are spectra of galaxies, but the signal to noise is extremely poor, signal to noise ratio of 2 or so. Maybe you need slightly higher signal to noise with SDSS kind of spectra. So you may not be able to do that with the galaxy as a background source. I mean, of course, there are some other issues of continuum fitting with galaxies. We don't know the continuum as good as quasar. So yeah, it could be challenging.
I have one question related to what Girish has asked. So why do you want to have these line of sights where galaxy surveys are sparse?
No, I don't. But they are.
Oh, okay.
Means,
yeah, at higher redshifts, you want to do it.
You need So if you so the idea is you want to measure 3D power spectrum, right? So you want to so if you have a gridded H1 observation, you want your sightlines to be mostly populated within the grid, and then you sort of do either interpolation or some sort of mimicking scheme to interpolate the density field or whatever to get the informations in the intermediate cells and do a cross correlation with the 21 centimeter space. Okay, so if your sightlines are very sparse, so that will introduce error, and reduce in signal to noise ratio.
Are there any further questions? Yes.
Thank you. Thanks, Suman, for a nice talk. So coming back to my question, I mean, did you or any other group, while doing this parameter estimation, try with other combinations, like say BAU plus SK or Pantheon plus SK, or a joint Planck BAU Pantheon?
Yeah, those
And
results are
what are the results say in terms of
Pantheon plus SK, I have
H naught value? I mean, does
about the H naught tension. So
Yeah.
I think the tension. So basically, in the load, where the tension lies between the very local observation and the very high redshift
Right.
observation, we do not have like a model independent H naught measurement of the 21 centimeter intensity mapping power spectrum in this local sort of system. But yeah, coming back to your question, are there like optimistic results or not? There are some results, but they're not that encouraging. Mostly lambda CDM. So okay, so like you can so because other like warm dark matter models and these models will affect you in much smaller scales where your noise from this interferometric observation will shoot up, and you don't have that much good observation measurement. Right. So yeah, so in reionization, you cannot very easily say that. Okay, it is difficult. So with the 6-parameter lambda CDM model and few like 4 to 6 astrophysical parameters, the problem in reionization becomes a bit difficult to tackle with to do parameter estimation. But which is not in the case of post-reionization. Here we can just say that okay, it's a bias vector of dark matter, and my power spectrum is simply modeled by this particular expression, and in that sense, it is easier to do a cosmological parameter estimation in post.
So if there are no further questions, we can move to the next talk, which is by